What we're going to do here is try to show you why the inverse trig functions look the way they do. Now here's the graph of sine. We know that in order to find the inverse function, we're supposed to switch the x's and the y's. Desmos does this actually in an incredibly easy way. I'm just going to switch the x's and the y's instead of solving, and then you'll actually see the problem. So all it did is switch the x's and the y's and graph them, which is great. Now remember, we're supposed to have an inverse function, and this new blue function over here fails the vertical line test an infinite number of times, right? So a long time ago, hundreds of years really, they decided to solve that problem by just erasing as much of the graph as they could and still leave enough so that it passed the vertical line test. So what I'm going to do here is I'm going to put a little slider in. I think I want to have the slider just go, say, from 0 to 6 so you can see what's going on. And what I'm going to do now, instead of having all of x equals sine y, I'm just going to have enough there. Let's see here, well, how about if I go from minus a to, let's see here, yes, is less than or equal to y is less than or equal to a. There we go. And so if I put a up at 6, you can see the whole graph at least appears there, which is good. Now what we're going to do is start erasing enough of the graph. So I've erased a lot of the graph here, but you can see it still fails a vertical line test. I need to take away more. I'm taking away more, take away more, take away more. There's still a little bit over on the right and a little bit over on the left. It still fails the vertical line test. So we're just going to go a little bit further, a little bit further, a little bit further, a little bit further. In fact, if you think of where we're going here, is that this point right here is actually corresponding to this point right here. Remember, this peak happens at pi over 2, and you can see that that's actually what's happening here. Remember, this is 1.57 something. So this is, if you go to your calculator and you graph arcsine, this is the graph you get, right? Now, because we erased so much of the actual inverse graph, it is not quite true that sine of arcsine equals is sine of arcsine of x equals x. So we won't try to use that as much as we have to. But that's why arcsine looks the way it does. Yeah, the next graph I want to do, normally I wouldn't do this, but I think arctangent is actually of the three the most important. So what I'm going to do is write y equals tangent x. And we saw yesterday that that has an incredible number of asymptotes. We want the inverse function. And you can see that the original function had a lot of vertical asymptotes. This inverse graph has just an incredible number of horizontal asymptotes. And boy, does this fail the vertical line test. So we're going to do the same thing we did before. I'm going to have my a, if I can get this actually over here, way over here up to 6. So I have the whole graph. And what I'm going to do is put this right in here, same way I did before. I'll say yes, minus a is less than or equal to y is less than or equal to a, like that. And it certainly looks like the whole graph is there, but we need to get rid of all these parts of the inverse tangent graph up here. So all this left passes the vertical line test. So I'm going to start pulling the slider back. So we're restricting. You can actually see that we're erasing part of the graph here. Haven't erased enough yet. Still haven't erased enough yet. I gotta get rid of all of that right there. I'm thinking, let's see, that's too much. Let's see here. Can I get 0.001 is about all I'm going to be able to do. I'm sorry. Yep. So you can see if you actually graph the graph of arctangent, this is what it does. And you can see that we only had to go up as high as pi over 2 and down to minus pi over 2. But arctangent is actually very important. It's more important than arcsine and arccosine. In fact, if you have a graphing calculator, almost everything on it depends on tangent and arctangent in just incredible ways. But that's how we get the graph of arctangent. I'm going to leave it to you to use this to find the graph of arccosine and give the domain and range from the graph you make.